Somewhere online right now, there's a video, and probably several more just like it, claiming that researchers at Google typed a question into a quantum computer, who built the universe, and that the machine gave back an answer so strange, so unsettling, that scientists refuse to talk about it publicly. It's a great hook. It's also, and I want to be straight with you about this from the very first sentence, not something that actually happened, at least not in the way those videos want you to imagine it. But stick with me, because the real story hiding underneath that fake headline is genuinely stranger, and in some ways more satisfying, than the myth itself. Because when you understand what a quantum computer like Google's Willow chip actually is, and what it actually did in a real published peer-reviewed experiment, you end up somewhere very close to that same enormous question. Who or what built the universe, just arrived at through real physics instead of an invented scene of a machine typing out a cryptic message. So let's start with the myth, take it apart honestly, and then follow the real thread all the way down, because it leads somewhere worth your time. The myth goes something like this. Google has a quantum computer so advanced, so powerful, that its own engineers don't fully understand what it's capable of. Someone, in some version of the story, a lead researcher, in another, an anonymous technician, types a philosophical question into it. The biggest question there is, who built the universe? And the machine, instead of returning nonsense or an error message, produces something eerie, sometimes described as a strange symbol, sometimes as a garbled phrase, sometimes as a value that shouldn't be possible for a computer to generate. The story spreads because it taps into something deep and human, the hope, or maybe the fear, that if we just build a machine powerful enough, it might reach past the walls of ordinary science and touch something genuinely metaphysical, an answer to the question every civilization in human history has asked in one form or another. Here's the problem, and it's not a small one. A quantum computer, including Willow, does not work anything like a chatbot. It has no language model bolted onto it, no capacity to parse an English sentence, no mechanism for turning a philosophical question into a response of any kind. A quantum processor is built to run mathematical operations on qubits, tiny quantum systems that can exist in blended states of 1 and 0 simultaneously, and to output the probabilities of different measurement outcomes once you run a specific, carefully designed algorithm. You cannot type who built the universe into Willow any more than you can ask that question to a thermometer and expect a philosophical answer back. The device simply isn't built to receive that kind of input or produce that kind of output. So no, nobody asked Willow who built the universe, and no, it did not respond with anything, cryptic or otherwise. That part of the story is fiction, dressed up to look like a leaked lab report. But here's where it gets genuinely interesting, because the reason that fake story spreads so easily, and the reason it feels believable to so many people even though it isn't true, is that Google's real quantum computing research has, in the last year, gotten close enough to some of the deepest open questions in physics that the leap to it's basically talking to God doesn't feel as absurd as it should. The real science is wild enough on its own that the mythical version almost seems like an unnecessary exaggeration once you actually understand what happened. In October of 2025, a team at Google Quantum AI, working with the Willow processor, ran an experiment they called Quantum Echoes. Rather than trying to have a conversation with the chip, they used it to do something far stranger and in its own way, far more profound. They used it to peer into the mathematics of how information behaves inside a chaotic, rapidly scrambling quantum system, the exact kind of system physicists believe governs the interior of black holes, and possibly the earliest, most violent moments after the birth of the universe itself. Here's how the experiment actually worked, in plain terms. The researchers took over 100 entangled qubits on the Willow chip and ran a sequence of operations designed to scramble information across the entire system, spreading a signal out until it looked, from any single measurement, like pure randomness, the quantum equivalent of stirring a drop of ink into a glass of water until you can no longer see where it started. In the middle of that scrambling process, they introduced one tiny, deliberate disturbance, a small nudge to a single qubit, and then ran the entire sequence in reverse, attempting to unscramble everything back to its starting configuration. If that tiny disturbance had truly vanished into the noise, the reversed system would have returned cleanly to its original state with no trace of what had been inserted. It didn't. An echo of that small disturbance came back out the other side, faint, buried in noise, but real and measurable, a signature of exactly how the disturbance had rippled outward and interacted with the rest of the scrambling system before being, in principle, retrieval again. This measurement has a formal name, an out-of-time order correlator, or OTOC, and physicists have wanted to measure it directly for decades because it's one of the only known windows into a phenomenon that used to live almost entirely in theoretical physics. The scrambling of information inside extremely chaotic quantum systems, the same kind of scrambling believed to occur inside black holes. and the same kind of scrambling some cosmologists believe played out in the earliest instance of the universe's existence, when everything that would eventually become galaxies, stars, and planets was compressed into an unimaginably hot, dense, rapidly evolving quantum system, the closest thing physics has to a genuine moment of creation that can be studied mathematically rather than just imagined. This is the part where the mythical clickbait story and the real science start to rhyme, even though the myth gets the mechanism completely wrong. Black holes, according to current theory, are the fastest possible scramblers of information in the entire universe, a kind of cosmic speed limit on how quickly a system can take information and spread it so thoroughly that reconstructing it from the outside becomes, for all practical purposes, impossible, even though the information is technically still there, encoded somewhere in the outgoing radiation. For years, this was almost entirely a topic for chalkboards and equations, something string theorists and quantum gravity researchers wrote papers about without any real hope of testing it directly, because you obviously cannot scramble an actual black hole in a laboratory. Willow's quantum echoes experiment gave physicists, for the first time, a small, controllable benchtop system that scrambles information in a mathematically similar way, and lets them watch with real experimental data whether decades of theoretical predictions about that scrambling behavior actually hold up. They did, with striking precision. So when people ask, in a roundabout mythologized way, whether Google's quantum computer has somehow touched the deepest questions about how the universe works, the honest answer is yes, in a very real and very specific sense, but not through some mystical dialogue. It touched those questions by giving physicists their first working, hands-on model of the exact kind of extreme, information-scrambling physics that cosmologists believe was at play in the earliest fractions of a second after the Big Bang, and that theoretical physicists believe governs the insides of the most extreme objects in the universe, black holes. That's not a machine answering who built the universe. That's a machine helping physicists test the actual mathematical rules that may have governed how the universe's earliest structure came to exist in the first place. Let's go a layer deeper into why this connects to cosmic origins specifically, because this is where the real story earns its own kind of goosebumps, without needing any invented mysticism to get there. Current cosmology holds that in the first unimaginably brief slice of time after the Big Bang, the universe underwent a period called inflation, an extraordinarily rapid expansion during which quantum fluctuations, tiny random variations at the smallest possible scale, got stretched out and magnified until they became the seeds of every large-scale structure we see today. Galaxy clusters, cosmic voids, the entire visible architecture of the universe. In other words, the very existence of galaxies, and by extension, stars, planets, and eventually us, traces back to quantum randomness present in an unimaginably hot, dense, rapidly evolving system in the universe's first instance, randomness that got amplified and locked in as the universe expanded. Understanding how quantum information behaves, scrambles, and gets preserved or lost inside extreme, rapidly evolving systems isn't a side curiosity to cosmology. It's arguably close to the central mathematical question underlying how the structure of the entire universe came to exist at all. Google's quantum echoes experiment doesn't directly recreate the Big Bang, and no responsible physicist involved with the project would claim that it does. What it does is provide a genuine, controllable, laboratory-scale system where the same category of mathematics, chaotic quantum information scrambling, described by the same kind of equations physicists use when they model black holes, and in some approaches, the universe's earliest moments, can actually be tested against hard physical measurements rather than left purely theoretical. That distinction between a system that recreates cosmic origins and a system that tests the mathematics believed to govern them matters enormously, but it doesn't make the achievement any less remarkable. Getting to directly measure, for the first time, phenomena that used to live entirely inside equations about the birth and structure of the universe is exactly the kind of milestone that makes physicists describe a result as landmark, foundation-shaking, or, in less careful hands, ripe for turning into a viral myth about machines whispering secrets about cosmic creation. There's another thread worth pulling here, because it connects to an idea that's become one of the most talked about concepts in modern theoretical physics. And it's part of why this specific area of quantum computing research keeps getting entangled, so to speak, with questions people associate with who built the universe. Physicists studying black holes discovered decades ago something called the holographic principle, the strange, still not fully understood idea that all the information contained within a three-dimensional region of space can, in principle, be fully described by information encoded on its two-dimensional boundary, the way a hologram encodes a three-dimensional image on a flat surface. This isn't a fringe idea. It emerged from serious mainstream work in string theory and quantum gravity, and it has reshaped how many physicists think about the deep relationship between information, geometry, and the structure of space-time itself. Some physicists have taken this line of thinking even further, exploring whether the entire universe's fundamental laws might be best understood not as objects moving through space and time in the traditional sense, but as an unfolding computation, information being processed and organized according to precise mathematical rules. This is not the same as saying the universe is literally a simulation running on someone's computer, a much more speculative and less mainstream claim. It is saying something more measured and, honestly, more interesting. That information and computation appear to be fundamental ingredients baked into how physical reality itself works, at the deepest levels physicists currently understand. Willow's OTOC experiments sit right at the intersection of this idea and hard, testable laboratory physics. They represent one of humanity's first controlled glimpses into scrambling behavior that theorists have long connected to black holes, to the holographic principle, and, more speculatively but not unreasonably, to the kind of information processing mathematics some physicists believe may underlie the fundamental structure of the cosmos. That is about as close as legitimate, peer-reviewed physics currently gets to the mythical question posed in the clickbait title, and it gets there not through some invented dialogue with a machine, but through decades of careful theoretical work in quantum gravity and information theory, finally meeting a piece of hardware precise enough to test it against reality. It's worth pausing here to be honest about the limits of all of this, because overselling the science would just be trading one kind of exaggeration for another. Quantum echoes did not prove what caused the Big Bang, did not identify a creator, and did not resolve any of the genuinely unanswered philosophical questions about why there is something rather than nothing, questions that remain, as they have for the entirety of human history, open. What it did was considerably more modest and also more solid. It gave physicists a working experimental tool for studying a category of physics, chaotic information scrambling in complex quantum systems, that happens to sit at the mathematical heart of some of the deepest theories we have about black holes, the early universe, and the relationship between information and the structure of reality. That's an enormous, genuine achievement. It's just a different kind of achievement than the machine spoke and gave us an answer. And understanding the difference is exactly what separates real physics from an engagement-optimized YouTube thumbnail. There's a reason, though, that this real story keeps getting dressed up in mystical clothing online. And it's worth understanding that impulse charitably rather than dismissively, because it comes from a genuinely old and very human place. Every culture that has looked up at the night sky has asked some version of the same question. What put all of this here? And for most of human history, the only available answers came from religion, mythology, and philosophy, because there was no tool capable of testing any hypothesis about cosmic origins against hard evidence. What's genuinely new and genuinely worth marveling at is that for the first time a tool exists, sitting in a lab in Santa Barbara, cooled colder than the vacuum of space, that can run real experiments touching directly on the mathematics some physicists believe governs how the universe's structure first came to exist. That is a profound shift, arguably one of the more profound shifts in the entire history of science. Humanity moving from purely speculating about cosmic origins to being able to run controlled, repeatable experiments on at least some of the mathematical machinery believed to underlie them. It's just that the true version of that shift is quieter, more precise, and more patient than a viral video claiming a machine typed out a cryptic warning about the nature of God. The true version requires you to sit with concepts like out-of-time order correlators, holographic principles, and non-equilibrium quantum scrambling, which admittedly makes for a less punchy thumbnail, but a far more durable and far more astonishing story once you actually understand it. So if you came here because that headline made you wonder whether we're standing at the edge of some machine-generated revelation about who or what built the universe, here's the honest, considered answer. No single machine gave anyone that answer, and probably no machine ever will, because who built the universe is a question about causes and meaning that sits, at least for now, beyond what any computation, however powerful, can directly resolve. But something did happen that deserves your attention just as much as the myth wanted it to. Physicists built a machine capable of running real, measurable experiments on the exact category of physics, information scrambling in extreme quantum systems, that connects directly to our best current theories about black holes, the holographic structure of reality, and the earliest instance after the Big Bang, when quantum randomness first got stretched and magnified into the seeds of every galaxy, star, and planet that would ever exist, including the one you're standing on right now. That's not a machine whispering secrets about creation. That's humanity building, for the first time, a genuine working instrument for testing the deep mathematics that may explain how creation, in the purely physical sense, actually unfolded. And once you understand that distinction, you may find, as I did, that the real story is the one worth telling, not because it's more shocking than the myth, but because, unlike the myth, every part of it is actually true. Let's spend a little more time with the machine itself, because understanding what Willow actually is helps explain both why the mythical version of this story is so easy to fabricate and why the real version is so hard to compress into a single viral sentence. Willow is a superconducting quantum processor, built from just over 100 qubits arranged on a chip small enough to hold in your palm, cooled inside a specialized refrigerator called a dilution refrigerator, down to temperatures a small fraction of a degree above absolute zero, colder than the emptiest, most desolate regions of interstellar space. At that temperature, the qubits, tiny loops of superconducting material, can maintain delicate quantum states long enough to run meaningful calculations, states that would be instantly destroyed by even the faintest trace of ordinary heat. Before quantum echoes, Willow had already made headlines for a separate but related achievement, demonstrating that adding more physical qubits to a properly designed error correction scheme actually reduced the overall error rate exponentially, rather than making things worse, a long-sought milestone that suggested truly large-scale, reliable quantum computers were an engineering challenge rather than a physical impossibility. Quantum echoes was, in a sense, Willow being handed a genuinely profound scientific question and proving it was stable and precise enough to produce a trustworthy answer, not through language, but through the careful, repeatable mathematics of physics. It's worth understanding, too, exactly why measuring an out-of-time order correlator is so difficult that it took until 2025 for anyone to do it convincingly on a system this complex, because the difficulty itself is part of what makes the achievement significant. To measure this rewind and compare effect, researchers don't just need a machine capable of running quantum operations forward. They need one precise enough to run an entire sequence backward, essentially undoing every single quantum operation in exact reverse order, with almost no accumulated error along the way. Any imprecision in that reversal shows up as noise that can easily swamp the very faint signal you're trying to detect, the small trace left behind by the original disturbance. Google's team used a clever trick, running a second-order version of the measurement, effectively performing the scramble and reverse sequence twice in a specific pattern, which amplified the faint echo enough to pull it clearly out of the background noise. That technical achievement, getting a signal this delicate to rise above the noise floor on a system with over 100 entangled qubits, is a big part of why researchers describe this as a genuine breakthrough rather than an incremental step. And it's also, not coincidentally, exactly the kind of technical nuance that gets stripped away entirely when a story gets compressed down into the machine gave a shocking answer. There's also a very concrete, very practical benefit to this technique that has nothing to do with cosmology or black holes. And it's worth including because it shows how a single piece of fundamental physics research can ripple outward into completely different fields. The same echo protocol used to measure otox turns out to be remarkably useful for a much more grounded application, extending the reach of nuclear magnetic resonance, or NMR, a technique chemists use to map the internal structure of molecules by studying how atomic nuclei interact magnetically with each other. Ordinary NMR has always had a hard range limit, since two atoms need to sit close enough together for their interactions to be detectable, which puts a ceiling on how much of a large, complex molecule's structure you can map in a single pass. Because the quantum echoes technique can amplify faint interference signals that would otherwise disappear into noise, it effectively extends that measuring range, letting researchers detect interactions between atoms that sit farther apart than conventional NMR can resolve. Google's team demonstrated this wasn't purely theoretical by running real molecular structure verifications on Willow and matching the results against known molecular geometries. If this scales further, and genuine scaling will require more qubits and continued advances in error correction, it could eventually give chemists a much sharper tool for designing new drugs, new materials, and new industrial catalysts. A very down-to-earth payoff from an experiment that also happens to touch some of the most abstract questions in theoretical physics. It's also worth sitting for a moment with why the scientific community's actual reaction to quantum echoes, measured and careful as it was, still carries a real undercurrent of astonishment, because that undercurrent is part of what the mythical clickbait stories are, in a distorted way, picking up on and amplifying. For years, out-of-time order correlators were almost purely a theorist's tool, appearing in papers about string theory and black hole thermodynamics with no realistic hope of direct experimental verification, because you obviously cannot scramble an actual black hole in a laboratory to check your math. Willow changed that by giving researchers a dial-in, controllable system where they could set the exact parameters of a scrambling process, the number of entangled qubits, the strength and timing of the disturbance, and then check, with hard data, whether decades-old theoretical predictions actually held up. They did, precisely. That's the part that makes physicists pause. It's one thing to trust an elegant equation written on a chalkboard. It's an entirely different experience to watch that equation, describing some of the strangest physics imaginable, play out exactly as predicted on real, noisy, imperfect laboratory hardware. There's a final piece of context worth adding, because it's genuinely part of why this specific area of physics keeps getting pulled toward questions about cosmic origins and creation in the public imagination beyond just being a naturally awe-inspiring topic. Some theoretical physicists studying quantum gravity have proposed that black holes sit at a kind of universal speed limit for how fast information can be scrambled, a limit derived directly from the same mathematics tested in Google's OTOC experiments, and that this scrambling speed limit may be deeply connected to how space-time itself emerges from more fundamental quantum information. Extending that line of thinking, some cosmologists exploring the universe's very earliest moments have used similar mathematical tools, describing the extraordinarily hot, dense, rapidly evolving conditions of the early universe using the language of quantum information, scrambling, and chaos. None of this constitutes a settled consensus theory of how or why the universe began. Cosmology remains an active, contested, and evolving field with serious, open questions and legitimate scientific disagreement about the earliest moments of the Big Bang. But it does mean that the mathematical toolkit, Google's quantum processor, just demonstrated it can measure directly, in a real laboratory, overlaps substantially with the toolkit theoretical physicists reach for when they try to describe how the universe's earliest structure came into being. That overlap is real, it's documented in serious peer-reviewed physics, and it's genuinely remarkable, which is exactly why it was such fertile ground for an invented mystical retelling in the first place. So here's where that leaves us, honestly, and I think it's a better place to land than the myth ever offered. Nobody asked a quantum computer who built the universe, and nobody ever will, because that's simply not a question any computer, quantum or otherwise, is built to receive or answer. But scientists did build a machine capable of directly testing the mathematics of information in chaos that sits at the theoretical heart of black holes, and quite possibly the earliest instance of cosmic history, the same instance when random quantum fluctuations first got stretched into the seeds of every galaxy, star, and eventually every person who has ever wondered looking up at the night sky what put all of this here in the first place. That's not a cryptic answer typed out by a machine. That's something better. Real, testable, repeatable physics, finally giving us a genuine foothold on questions that, for the entire history of human civilization, could only ever be imagined. And maybe that's the part worth sitting with longest. The myth wanted you to believe a machine had somehow shortcut its way to an answer humanity had never earned, a kind of stolen glimpse behind the curtain. The real story asks something more patient of you, and in the end, offers something sturdier. That the biggest questions we have don't get answered in a single dramatic instant, typed up by a blinking machine in a darkened lab, but assembled slowly, honestly, one carefully verified experiment at a time, by people willing to spend a decade building a chip cold enough, precise enough, and stable enough to test one small, specific piece of the puzzle at a time. Willow didn't tell anyone who built the universe. It did something arguably more remarkable. It handed physicists a working tool to keep asking that question properly, the way science actually answers things, not with a single mystical reply, but with evidence, patience, and the slow, cumulative work of getting a little closer to the truth than we were the day before.